Okay, so I think it's a good time to start. So hello and welcome everyone. This is week 6 of the live discussion sessions for the course Foundations of R Software. And this week we'll basically continue diving deeper into the control structures in R. So I'll start by sharing my screen, and as always, please let me know if you can see my screen and if I'm audible. Please confirm these two things. Can you see the R Studio window?
Yes, sir, we can.
Okay, very well. So when we speak about control structures, what we mean is how the execution of a program happens. So one of the ways is through conditional statements, where we want our program to proceed in one direction if certain conditions are satisfied, or in a different direction if some other condition is satisfied. Or sometimes we put a default condition. If none of these special conditions are satisfied, we just want to do some generic steps. So that is achieved using if, else, else if, those kinds of commands. So conditional statements are basically related to decision making within the code. Now, in addition to this, there is another important construct that is known as looping. So this is also sometimes referred to as repetition. Maybe I've spelled it wrong. But anyways, so looping or repetition, or in some text books you can also see the word iteration. So that basically means you have some set of commands that you want to do again and again. Now, of course, it can be as simple as just going through a list and applying an operation on each member of that list, or it could be a sequence of commands where you do some calculations in between. But why are loops important? So let's say I design a I want to print the numbers from 1 to 10. So the most straightforward way of doing that is just I write print 1 and print 2, print 3, and I'll keep doing that till I get all 10 numbers. But that sorts of, in some way, this defeats the purpose of coding, because one important purpose of writing codes is to automate some behavior. So you want the computer to do something that you would have done, but you also want the computer to do it in a way that saves time and space. So writing print the print command 10 times to print 10 numbers is not really taking advantage of the programming environment. So that's why we have control structures, looping control structures. Now there are different ways in which these can be implemented. So we'll take a look at them. So one is the for loop, the while loop, then there's something called the repeat loop. So let's look at these one by one, and also let's try to highlight the differences. So which one do we use in which situation, or what do we need to know from before? So as usual, let's define a vector. So let's call it vec1, and this will be just the numbers from 1 to 10. Now, the way a for loop works, so for any of these control structures, whether these are if-else statements, loops, functions, or even some higher abstract quantities, what we need to know is their syntax. How exactly do we write them? Now, for the time being, we are doing everything in the console. So we'll try to see. So when you write them in a script, it's more straightforward. So you can arrange things in different orders, or you can manage the spaces as per your need. But when we're writing it in console, there are a few things we need to be careful about. So I'd like to repeat this once more. As we have seen previously, that if we write an operation on the console that expects something on its left side, something on its right side, so like addition. So So addition expects two arguments. So we're given 12 plus, and then we are not giving anything. Then R expects us to supply that argument. So even if we press enter, it will not do anything. It will just ask us for more input. So now if I put 12 plus 13, it basically gives us 25. So basically what I'm trying to revisit here is the concept of multi-line statements. And these multi-line statements are important when you are trying to write long statements. So for example, how does a for loop work? So for loop, the syntax is you mention a dummy variable. So let's say I call it x. So x is a dummy variable which would represent all the entries inside vector 1. Okay, so in the chat there is a question if we write vec1 equals 1 colon 10, and if we write vec1 as the collection of 1, 2, 3, 4 up to 10, then these are two different things. Yes, these are two different things. The reason being, in the first case, it is automatically treated as integer. So 1, 2, 3, 4 up to 10, these are all integers. But when you make a collection, C 1, 2, 3, 4 up to 10, then by default these are treated as decimal numbers. So okay, I'll come back to the for loop. So let me spend a brief minute on this. There's one way to check. So you use this as dot integer command, and you apply this on vec1. Oh, sorry, is dot integer, not as dot integer. So it says true that vec1 is an integer. But if you define something like vec2 is a collection of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And now if we ask, is vec2 an integer? It will say false. Because when we make a collection like this, these are automatically stored as decimal numbers. So it's actually 1.0 instead of 1, 2.0 instead of 2. But if we want to define these as collections and also want them to be treated as integers, you put this capital L next to each of the numbers. So now if you ask is vec2 an integer, it will say true. Now this distinction is done because whatever you put in a collection, so in R we do not explicitly mention, what type of data type we are working with. R does that interpretation for us. So in the collection it could be anything. It could be decimals, it could be integers, it could be string, all sorts of things. But when we are defining this 1 colon 10, what we are asking for is a sequence of numbers from 1 to 10. And since we have not specified what is the step size in that sequence, R automatically takes that step size to be 1 and treats everything as an integer. So it's 1, 2, 3, 4 up to 10. Because the reason for treating them as integers is that if R had treated them as doubles or floats or decimals, it's not clear what step size should have been taken. It could have been 1, then 1.5, then 2, then 2.5. But it could also have been 1, 1.2, 1.4. So there is that ambiguity. But if R treats them as integers, it's quite clear. You take 1, 2, 3, 4 up to 10. So that is why defining 1 colon 10 and defining this collection from 1 to 10, these are two different things. But one suggestion from my side is whenever there is a confusion, use this is dot integer or is dot double, or depending on what you want to check. So it's always good to check that what you have defined is exactly what you intended to define. And if it's not the case, then you can do conversions. Basically, you can use this one as dot integer. So if you check is dot integer for vec1 and it says false, but you wanted vec1 to be an integer, you just convert it and either store it in a new variable or maybe update the same variable. So depending on your use case. Now, coming back to the for loop.
Sir?
Yeah.
Sir, so this vec1 will be a vector quantity, right?
Vec1 will be a vector quantity, yes.
So when we use C, then it is not a vector quantity. Only it is vector quantity when we use L inside C.
No. In both cases, it is a vector. But when you use C and you use numbers, so this definition, rewrite this. So for example, let's say if you're writing vec3 c, so 1 3 5 7, these 4 entries, it's still a vector, okay, but this is a vector of doubles, not integers. So that's why here instead of int it says num, so a number. But a number can have a decimal part as well. Okay, that is the distinction in R. That integer is does not have a decimal part, but number can have a decimal part. Is that clear?
Okay, sir.
Okay. So now coming back to the for loops. So the way you define for loops in R. So first of all, when do you define for loops in R? So like I said, looping is actually sort of repetitive statements. So you have a bunch of statements and you want to repeat them again. Maybe you want to modify something very small within them, but at large you want to repeat a set of statements. So you use a for loop when you know how many times you have to repeat. So let's say what we want to do is maybe print just all entries inside vec1. Okay, so what we'll do is we'll just define this dummy variable, temporary variable, or in other words, local variable, because this variable will be active only inside the for loop. So I'm saying for x in vec1, this will apply to all elements of vec1. Then I want to put these curly brackets, and within the curly brackets I want to say what I want to do. So let's say I just want to print it. Now like I said, we use for loops when you know how many times we want to repeat. So here we know the number of times the repetition will occur is the length of vec1. So if I know the size of vec1 and I want to apply an operation on each element of vec1, then I can use something like this. Because I know vec1 has a fixed size, because I defined it previously. So if I do this, you see, it just prints everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe if you do the same thing with vec3, it's 1, 3, 5, 7, the elements of vec3. So you see the advantage. Just one line of code is sufficient to print these 10 numbers. I don't have to say print 1, print 2, print 3. And the real advantage comes when the size of the vector is very large. So let's say I have something like vec4, it goes from 1 to 1000. Now you can imagine how long it will take us if we started writing print 1, print 2, print 3 up to print 1000. So that is not practical. So even if we have something as large as this, the same line of code, okay, it does the same task and it does it at a quite good speed. So this is the advantage of for loops. Now we can make it more complicated. So a for loop doesn't have to be just a simple printing tool. So you can do more. I mean, of course, you can always print if that's what you want to. I mean, if you want to check the output after each repetition. But another thing that you can do is, let's say, okay, let's take x in vec1. Now remember what I said about multi-line statements. So I want to write more, so I will not write everything in a single line. I'll just press enter here, and then I'll write for, I'm defining another dummy variable for y in vec1, let's say, or let's say we just work with the smaller one. Let's work with vec3, and then what I want to do is I want to print x times y. Now you see, R is still expecting some more output. This is for a very simple reason. Can someone point out why R is still showing a plus? Why my command is not complete?
Sir, outer for loop is not closed.
True. Okay, so now this is closed. Now you see. So what this structure is called is a nested for loop. So this is a for loop within a for loop. And what I'm doing is I'm taking variables from two different vectors and performing operations on them. So the way this will run is it will select the first element of vec1, which is 1. Now it will start looking into vec3. So it will run the repetition through vec3 and execute this command before updating x. So in the beginning, x equals 1, which is the first element of vec1. Now for y in vec3, so the first element of vec3 is also 1. So the first thing that is printed is 1 times 1, which is 1. Then it updates y. The y now becomes 3. So 1 times 3 is 3. Then y becomes 5. So it's printing 5. Then y becomes 7. It's printing 7. So now, for a single value of x, I have gone through all values of y. So the next step is to update x. So now x becomes 2. And again I go through vec3 one by one. So 2 times 1, 2 times 3, 2 times 5, 2 times 7. And this will keep happening as long as there are elements in vec1. So this is how nested for loops work. Is there a confusion with respect to this?
No, sir.
I must tell you that if you change the order, so if you say for y in vec3 first, and then if you say for x in vec1, and then let's say we are printing x into y, now we can close it here only. See, now the way things are getting printed is different. So this is not interchangeable. So that is something that must be kept in mind, because we have selected some element of y, which is 1. Now we'll go through each element of x one by one and do the multiplication. So 1 times 1, 1 times 2, 1 times 3, all the way up to 10. So now that vec1 has been exhausted, then we go back to vec3 and update the value of y. So now y becomes 3. And then we go through vec1 again. So 3 times 1, 3 times 2, 3 times 3, all the way up to 3 times 10. So this should be kept in mind, that if you interchange the for loops, the output will be different. I mean, there may be special cases where it is not. So for example, if I had said, okay, for y also in vec1, x also in vec1, then vec1 and vec2 have the same size, they have the same elements, so it doesn't matter what order you do the operation. So it would have given the same output. But in this case, it is different. So now we have seen that we can nest loops with loops. The next generalization is that we can nest conditionals within loops. So let's say we want to do a sort of filtering, that we go through x. So x is in vector 1, and what we want to do is we want to check. So if x is greater than 2, then print x, else print 0, let's say. So you see, we have put a condition inside. So while the iteration, or we'll go through each element of vec1, but the operation is different depending on what number we encounter. So for the first one was 1. So we see that this condition, x greater than 2, is not satisfied. So the statement next to else will be executed. So 0 is printed. Second one is 2. Again, 2 is not greater than 2. So again 0 is printed. But afterwards, we have 3, 4, 5, 6, all of them are greater than 2. So those numbers are printed. Now, through this, we can also introduce another useful function which can be used inside the print command. And this is something known as paste. So let's say we want to check explicitly which numbers are even and which numbers are odd. So we're saying if x when divided by 2 gives 0 as the remainder, then what we want to print is, I'll explain what this paste means. So x is even. Else we'll print is odd. So you see, again we are trying to filter out which numbers are odd, which numbers are even. It's a simple loop which does a very simple task. So you can see, if x gives a remainder of 0 when divided by 2, obviously that's the definition of an even number. So that's what we are printing. Otherwise, we are printing that that number is odd. So the contents of vector 1 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So alternatively, we get 1 is odd, 3 is odd, 5 is odd, 7 is odd, 9 is odd. But 2, 4, 6, 8, and 10 are even. Now, what I wanted to emphasize was this paste command. So this paste command is useful when you want to print a combination of numbers and strings. And this is even more useful when you don't know the value of the number. So for example, what I've done here, so x is even, so x is not just a number. So I could write, let's say 4 is even, and that is fine because I already knew that I wanted 4 to be here. But in that case, maybe I did not even need the paste command. So I could have just said print 4 is even. But if you want to do it with a variable, and if you do it like this, it will just write x there. It will not replace the value of x with, it will not replace the variable x with its value. So that's why this paste command is useful. So you can give a variable, so you can even give two variables. So you can write something like, let's say, let me define s1, the first string, it says hello. S2 is the second string which says world. Now if I do paste S1, S2, it will just become hello world. So that is the advantage of the paste command. And you can use it from inside the print. So you can just say print and then paste, and then let's say S1 and X. So if you remember, the loop went through the elements of the vector 1, and the last element of vector 1 was 10, so that's the value that X has retained. And if I do S1 comma X, it just becomes hello and 10 that gets combined. So that is the usefulness of the paste command. Now there are a couple of more things that are relevant when we talk about loops or iterations and so on. Because what we have done so far is we have gone through each element. What we have not done is something called skipping an element, or another thing which is known as breaking out of the loop. So it may be possible that you don't want to, if you're working with a very large vector, you only want to look at first 50 entries or so. So let's say we had vec4 which had 1000 entries. So if I say for x in vec4, so first I will check if x is greater than 50, then we'll break. Otherwise, we'll just print x. So what this break command does, it basically exits the loop. So this is useful when you don't want to work with the entire vector, you only want to work with a small piece of it. So you can suitably put a break command there. Or let's say you have some input which contains, let's say, even numbers. So you did not want any odd numbers in that list. So you can put a check like this, that the moment an odd number is encountered, you break out of the loop. So that means there is some error in the data entry. So that's the usefulness of the break command. Another similar command, which does not actually break out of the loop, but it skips command execution, is what is known as the next command. So let's say again we work with vec4, and what we want to do is that we want to skip all numbers which are divisible by 5. So okay, let's put more if statements this time. So if x is greater than 50, then we break. Else, if x is divisible by 5, then we just skip the loop. Else, we print. So let me come back to this. So you see what is happening here. We have already implemented this break statement, which essentially, takes a piece from your vector. So we don't want to work with all 1000 elements of vec4. So we put this break statement that the moment the value of x grows above 50, we'll exit out of the loop. That's why you don't go beyond that. But we have also put a skipping command, that if I find a number which is divisible by 5, that's another way of saying that if I divide that number by 5, I get a remainder of 0. Then I move on to the next number. So I don't do any operation with this. And if none of these conditions are true, then I just print the number. So I start with 1, I print 1, because none of these two conditions are true. Then same thing with 2, 3, 4. But the next element is 5. So 5 satisfies this criteria, that 5 divided by 5 gives you a remainder of 0. So I don't print 5. I just move on to the next one, which is 6. So again I go 6, 7, 8, 9. I encounter 10. I again execute this next command. So 11, 12, 13, 14. So you see, we have printed numbers which are from 1 to 50, but we have skipped numbers which can be divided by 5. So these are some important constructs that you should know when you are trying to work with loops. So now we move to a second variety of looping construct, which is known as the while loop. Now, the most basic way in which the while loop differs from the for loop is that for the for loop, you already knew how many times, what is the maximum number of times the loop will be repeated. Now, of course, with the break and next commands, that number comes down, but you still know the maximum number. So if we were looping through vec4, we know that if I don't put any break or next or anything like that, it will go for 1000 times. But sometimes it is possible that I don't know how many times the loop will run, because the execution of the statements influences the condition that is required for the loop to progress. So let's say I start with a number, I equals 0. Now I want to put a command while I is less than 5. Then I want to keep printing I, and nothing else. Let's say that's all I have written. Now can you guess? So there is a problem with this code. So there is no syntax wise it's correct. Logic wise also it is fine, but when you run it, there may be one issue. So Can anyone guess what that issue could be before I execute it here?
You are not incrementing I value.
So what will happen because of that? So because you know, in a loop, it tests the condition and then executes the statement. Then it comes back and tests the condition again. Then executes the statement again. I mean, depending on if the condition is true or false. So if I'm not changing the value of I, so let's start simply. So I equals 0. What will happen in the first instance? Is I less than 5? I mean, is it or
Yes.
is it not? It is, right? 0 is less than 5. So print I will work. What will happen in the next instance when I again come back to test the condition? Go ahead, answer this. I mean, anyone. It's a very obvious thing. So
The loop will run infinite time. It
the
will
loop runs an
because I
infinite
will
times because I'm not
not there.
changing I. So the same condition is satisfied every time. So the statement will keep on going. So you see this blinking zeros. That means it's just getting printed, 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 printed. So this is. So I can break out of this infinite loop using a control plus C from the keyboard. But this is one of the pitfalls that if you are not careful, you may end up writing a infinite loop. Problem with the infinite loop is it will keep running, it will keep running, it will not show any desired behavior, and it will end up hijacking all of your RAM. So that's something we want to be careful about. We don't want to, get stuck with an infinite loop. Okay. So if I check, I is still 0. So this is also one difference between for loop and while loop. Because for loop, it was always something in a vector or something in some other thing. So that way, the values were getting updated by the for loop itself. But in case of the while loop, we have to do the updating ourselves. So you can write print I, and after printing I, we just put I equals I plus 1. So we change the value of I. Now if I do it, it gives me the proper answers. So it was 0 in the beginning. Is it less than 5? Yes. So it will print 0. Then it will increase the value of I by 1 unit. So 0, 1. Now it's 1 is less than 5. Yes. That will get printed. So it will get printed as long as this condition is satisfied. After printing 4, I equals I plus 1 makes I into 5. So 5 is not less than 5. So the loop will be terminated. Now, of course, another way of terminating out of the while loop is the break command. So that is also possible. Now, one thing I wanted to show you, I wanted to introduce an example. Let's say sometimes, so here also, we know, I mean, this is not actually a while loop. Even though we have written it like a while loop, this is more like a for loop. Because we are incrementing the values by 1, so we could have just defined this as a vector and then printed each of the entries. So the vector could have contained 0, 1, 2, 3, 4. And I would have said for x in vector, print x. And it would have printed these values. So where while loop is especially important is when we don't exactly have a, control on how the value of these test variable will get changed. So I'm saying, let's say I equals sample. I'll use this sample command. Now let me open this script file. I'll come to what a function is, but let's look at a sample. So what sample does is that from a vector, so here bones equals 1 to 6 is a vector. It basically, you tell it how many times you want to pick values from that vector. So in this command, what I'm doing is I've defined this vector bones which is just 1, 2, 3, 4, 5, 6. And I'm saying that take values 2 times. And replace equals true means that after you have taken that value, you are allowed to repeat that. So if I'm taking from 1, 2, 3, 4, 5, 6, let's say in the first instance I take out 5. Then if you say replace equals false, then that means 5 will not be considered when you pick a second number. So for the second number, the choice is 1, 2, 3, 4, 6. But if you make replace equals true, then 5 can be considered again also. So let me close it. I'll come back to this soon enough. So let's just make it 1 to 10. And I only want to pick one number. And I'll put replace equals false because I don't want to repeat anything. And then I'll just say print I. Okay, now if I run this, nothing happened. So can anyone guess what would have happened that nothing got printed? So let me repeat what this sample command does. Okay, so let me just show the action of the sample command. So it can give me numbers from between 1 to 10, and it is giving me one number. So this is like rolling a die basically. So if I make it from 1 to 6, it's a 6-sided die, and I'm just rolling a die and getting some numbers. So when we did this, nothing got printed. So can you guess what might have happened that nothing got printed? Because last time at least 0 was getting printed. This time even 0 did not get printed. Can you notice some difference between this while command and this while command? Anybody? There's one very obvious difference between these two. Okay, let's talk about similarities. What is similar between these two loops? Start from the first line. What is happening here?
Both the conditions are same.
Both the conditions are same. So okay, that is a similarity. Then look at the second and third line here and second and third line here. Is there a similarity or is there a difference?
There is a difference.
There is a difference. What is the difference?
The sample generates some random values.
Yes, but even without getting into the sample, the difference is I'm printing first, then updating the value of I. Here I'm updating first, then printing the value. So because of this, if I started with I equals 0, this 0 was always going to get printed. Even if I had put I equals I plus 10, in which case this condition would have been false in the second check itself. But here, I am changing the value of I first before printing it. Now my condition says while I is less than 5. So now can you guess what would have happened as a result of this sample that nothing got printed?
The sample might generate the number which is less than 5.
Right.
Sorry, greater than 5.
Right. So again, these are the kind of things we need to be careful about, that how we are updating, when we are updating. So loops have 3 important components. The first one is the condition that is tested at each iteration. The second is the update command, how we are updating our dummy variable. And the third one is what exactly are we doing, I mean, in the rest of the statements. So there is another simpler loop, which is just repeat. Now, repeat does not take any condition into account. It will just do something again and again. So let's say I put repeat print 5. It will just keep printing 5. So the default behavior of repeat is to generate an infinite loop. Okay. The way we can use it in slightly different manner. So let's say we have our vec1. And we just say, okay. So what we want to repeat is these bunch of statements. So I say, what variables do I have? I have x, I have I. Let's work with I. Repeat, and then we print I if I is greater than 10, then we break. Otherwise, I equals I plus 2. So we want to repeat this. We start by printing I is 5 and we check the condition. But mind you, this if else is not a default statement inside of repeat. This is something we have put in by hand. And using this, we can basically make repeat behave like a for loop or a while loop. But let's say the utility of a repeat loop is, let's say you just want to take some input from the user. So you have written a system which takes in some orders, maybe food orders or something. So you don't want to put a limit of how much a user can order. You can't tell the user that, okay, you can only order 5 items. So the user will keep adding entries to his order, and then you will suitably put a break statement. So you will basically tell the user that, okay, if you don't want to order anymore, just enter the number -1. So if you see the number -1, we'll just break out of the loop. Now to demonstrate that, we'll have to first look into functions. And as an example of functions, maybe we'll see a user input case. So you have already seen functions. So the first question is, why do we need functions? So I remember in the early sessions, I think week 1, week 2, there was a lot of discussion around why do we need libraries. And the answer was basically, you don't want to load everything that you don't even need in every session that you work on. So a lot of useful tools, useful functions, useful methods, these are packaged together in some libraries, and you can use them when you need them. But an even more basic question is, so we have seen why we need conditionals, we have seen why we need loops, but why do we need functions? And what is the purpose of functions? So functions again allow you to repeat your code, reuse your code without rewriting your code. So when I simply say print x, something is happening in the background. So for me, it's as simple as print x, or if I say, let's say, mean for vec1, I simply put this command, I get an answer. Or even this collection operation, which I do, let's say 1, 2, 3, and I call it z. Something happened. A variable was created which has a vector-like behavior and stores 3 numbers. So all of these are complicated functions, but that complication has been hidden away from us. So we don't really need to know what is happening at the back end, because if you want to make this complicated, I mean, you just overthink about this and you'll realize how complicated this is, because this is a computer screen. This is made up of some electronic signals. There's a lot of pixels involved here. So even how color is being represented here, how exactly I'm typing from a keyboard. When I press P, a P is shown here. The word that I write is exactly reflected here. So I want that word to convey a certain meaning. That exact same meaning is understood by R, and then ultimately it's printing a number. So this is a very complicated operation. But even if we stay away from the low level operations, something as surface level as this, taking a mean, which is what? You add each of the elements of the vector and divide by the total number of elements. So you don't have to do that, right? So now you can use this mean as many times as you want. So you can maybe do the mean for vec 2. You can do the same for vec 3 and vec 4. So that is the benefit, that inside this, the definition of this function, there are some complicated steps are going on, but we don't have to rewrite it again and again. Because first of all, it would not be possible to remember, the details of each of these functions. And second of all, we'll waste a lot of time just writing simple code to do something simple like this. Then we will not get time to write more advanced code to do advanced tasks. So similarly, when you are writing your own code, you can define your own functions, basically user-defined functions based on your need. So let me reopen this function demo.r script file. And again, with the use of sample, which is an inbuilt function, sum, which is also an inbuilt function, let me show you what is happening here. So first of all, I'm defining a function called roll. And this is supposed to copy the behavior of rolling a dice. So we are working with a 6-sided dice. Now, how do we define a function? So if you remember, we can define variables in two ways. I can say x equals 5, or I can put this arrow from the value to the variable and say x is 6. Similarly, to define functions, you can put an arrow or you can put an equal to sign. Now, functions can take arguments. So what are arguments? So when I said take the mean of vec1 was the argument. Now maybe I want to take the mean of two numbers, 1 and 2. This will just... So these are basically the arguments. Or if you remember this paste command, so if I do x s1 6 hello, so these are arguments. Now, to make your job easier, or to make the job of those who are using your code easier, you can give names to these arguments. So here, bones is the name given to this vector. What is this vector supposed to represent in my function? This is supposed to represent a dice. Now I'm working with a 6-sided dice, but you can maybe work with an 8-sided die or a 20-sided die. It doesn't matter. Now, the value that is given here, so I could have just left it as bones. I did not need to provide a value from the beginning. But if I am providing a value, then that value is treated as the default value. So if the user doesn't provide any values, it will automatically be assumed that we are working with a 6-sided die. Now, using this argument, we'll execute some commands inside the body of the function. So what am I doing? I'm executing this sample command. The first argument is what you want to sample from. So I want to sample from this vector which I had named bones. How many numbers do I want to sample from it? It's 2. I want to pick. So basically what this function does is, you can think of it as rolling 2 dice, noting down the numbers on each of the die and then adding them. And replace equals to true. Again, replace is an argument for the sample command, which, as I mentioned previously, if you set it to true, the same number can be sampled again and again. Okay, so before moving on to this role biased one, we'll just source this. So if we source this, what happens is that this function is available in our console or in our session. So now here's what I can do. I can just say roll and not give anything, give no arguments. Then it is assuming that I'm working with a 6-sided die and it's picking out 2 numbers and printing out their sum. So you can see it gave me 9. Those numbers could have been 3 and 6, 4 and 5. We don't know that, but we could modify our, function. But this function basically rolls 2 dice and gives you the sum. And again, if I am not giving any arguments, the assumption is that we are working with a 6-sided die, because that is what we have written here. But if I remove this, or before removing this, let's work with this only. So let's say if I'm working with a 10-sided die, you can get even larger numbers. Because remember, for a 6-sided die, the maximum number you can get is 6. If you get 6 on both, you can get 12. Now we are getting 14 also. So that means that is the modification of working with a die with a larger number of faces. But now if I remove this, I'm not giving a default value. I save this and then I source this. So now if I say roll and don't give any arguments, this will return an error, because it expects some value from the user, because the person who has written the code has not given any default values. So now if you want to work with a 6-sided die, you have to explicitly mention that you are working with a 6-sided die. So is that clear? I mean, the syntax for defining a function, giving arguments to that function, giving names to those arguments, and also giving default values. So if that is clear, then I'll just highlight this simple extension of that previous example, which is the rolling of a biased die. So let's see. Everyone can see the full line, right? Hello?
Yes, sir.
Okay. So there is nothing different with respect to how the function has been defined. Only one difference has been added with respect to the sample statement or sample command. So what you can do, there is another argument that you can provide for the sample command, which is called probability, which is written just as prob. And you can give a vector of numbers. Each of them has to lie between 0 and 1. So basically a fraction where the numerator is smaller than the denominator. But the sum of all these should be equal to 1. And the number of entries should actually correspond to the number of elements in this vector. So if I'm working with a 6-sided die, I need to provide 6 probabilities. The sum of these probabilities should be 1. And what happens because of this biased rolling? So normally, if you say, again, since R is a statistical tool, we should talk about probability and statistics. So, of course, if you flip a coin has 2 faces, heads or tail. If you flip it once, you'll get one of them. You flip it twice, maybe you will get 1 head, 1 tails, maybe you'll get 2 tails, maybe you'll get 2 heads. But there's this law of large numbers which says that if you flip it, let's say a very large number of times, like 10,000, 1 million times, then chances are that almost 50% of the times you'll get a head, almost 50% of times you'll get a tail. So, but if you are working with a biased coin, or in this case a biased dice, so same thing applies for a dice. If you are rolling a six-sided die for a very large number of times, then the probability of obtaining a 1 or 2, 3, 4, 5, 6, that should be equal. So 1 by 6th time you should get 1, 1 by 6 times you should get 2. This will not be exact, but this should be approximately followed. Now this will be exact if you can repeat the experiment infinite number of times, but that is not practical. So we only work with approximations, this large number, law of large numbers. But if you have a biased die, it will favor basically giving you the entry which has the larger probability. So let me change this slightly. Instead of sampling two of them and giving the sum, I'll just return the number dice. So let me save this and source it again. And so let's work with six-sided die. I'm not giving any other arguments. So now, if you print it here, now of course you can't see whether this biased behavior is reflected or not, because maybe we'll just print it 10 times, maybe one never comes up in those 10 times. But this biased behavior will show up if you do this for, let's say, 5,000 times or 10,000 times. And again and again, what I'm trying to emphasize is working with large data sets is actually very common when you are doing statistical analysis. So all these small experiments that we are doing for small number of iterations or small vectors, these are just to understand how things work. But if you look at practical applications, you'll always work with large data sets, especially in R. So in such cases, biased behavior may show up sometimes. Okay, so I'll close this. And the last topic that was discussed in this week's lectures is that of a sequence. Sequences in R. So now remember, we always come back to this example from 1 to 10. And when we do that, or let's say 1 to 15 or something, and we know that when we explicitly define a range like this, we get integer values separated by 1 unit. Now we have seen that we can also do the same thing this way and go all the way up to 15. And in that case, these numbers are not stored as integers, but they are stored as decimals. But what if we want a simple command to just generate decimals which are separated by a fixed step size? That step size need not be integer. So I don't want integers. I want some numbers. So for that we can use what is known as the sequence command. And the sequence command, so it's a generalization of this range-based definition. So I can repeat this. You can say from 1 to 15. It will again give me those numbers from 1 to 15. Now if I do the opposite, from 15 to 1, it will give me the numbers in opposite order. If I do 15 to 1, again does the same thing. But what we wanted to change was the step size, which we could not do when defining the vector using this colon notation. So we can add another argument for this function, which is by. So if I increase by 2, so I want to go from 1 to 15, but the increment or the increase has to be by 2. So it's 1, 3, 5, 7, 9, 11, 13, 15. Even better, I can do it by 2.5. Now of course, one thing to keep in mind is if the step size is such that the last entry is never touched upon, then that will not be added to the sequence. So because starting from 1 and increasing by 2.5, we go up to 13.5. If we add 2.5 more to it, we'll get 16, not 15. So the sequence is stopped here. So this final entry, which is the value for 2, it may or may not be a part of your sequence, depending on how you're defining the sequence. The good thing about sequences is you can define them in either order. So let's say I want to define from 10 to 0, and I'll put my step size minus 2.5. So it will just decrease them. And as always, you can store this sequence in some variable, and then you can check whether this is integer or not. Now, of course, this is not integer because of this 2.5, the entries have a fractional part. But if we do this one and store this as var2, again it comes out as false. So that's another difference between this colon based definition and this definition through sequences. Because for sequences, if I check the type of var2, it will give me double. So just like this C 1 2 4 7 whatever, just like this method of defining a vector defined these numbers as double by default, not integers. Similarly, when we define using sequences, we get doubles, not integers. And of course, you can convert by using as.integer. One more thing to check is whether vectors and sequences are the same things or not. So if I do is.vector, it's true. So this can also replicate all the behavior that a vector has. So this was a quick summary and also a walkthrough of these various control structures. Functions, how do we define functions? So we also discussed nesting loops within loops, nesting conditionals within loops. So this was all I wanted to discuss in today's session. If you have any doubts, please feel free to ask. If not, then I can end the session here. Okay then, I'll see you guys next Saturday on